wave velocity and compression wave velocity measurements in the saprolite or in the 2B saprolite. As far as I know, these low strain values in 25428 were not used in any of the analyses. We basically kept to the values of Poisson's ratio measured from the VP and VS measurements.
Okay, so you measure Poisson's ratios in the SSI.
Yes. Measure Poisson ratio or what high strain, a high strain, low strain, right?
Low
A low strain. Yeah, that's what I've never heard of high strain.
Well, that's why.
So there is only low strain Poisson ratio.
Yes.
Because I've never heard of Poisson before. And just calculate whatever you see.
Well, you measure yes, and you back calculate what the
You can only measure low strain, right? You can do CAT. You can get the high strain. That table has to run you're confused. So to clarify it, we can do, once you set them up, you set the price, and then you measure and keep the deal. It depends. I'm saying that it, I'm not saying you are doing it. Okay.
All right.
Okay, we understand. Okay, it's separate.
Can we go to the next one? The next question wanted to clarify about the NEI check for RBSD and control building. First, explain if the NEI check for partial column outcrop pairs is performed using full column best estimate lower bound and upper bound profiles. Then the question is asking us to explain why envelope of surface ARS for full column outcrop pairs is substantially higher than those of the partial column outcrop pairs. Then the question is asking us to explain the differences between PBSRS in FSAR figures 371, 212, and 213, and those of the figures 216 and 217. And finally, explain whether in situ or backfill properties are used in performing the NEI check and provide the technical justification. So in our response, we'll point out that the whole purpose of doing the NEI check is the consistency, again, between the site response analysis, which is done probabilistically, and the SSI analysis, which is done deterministically. So when you're doing the check, you have to do it within the consistent sort profile. So if you're doing an NEI check for partial column pairs, the partial column pairs is calculated by removing the top soil, but the pairs is still calculated somewhat lower than the surface because you still have some depth of rock on top of your foundation. Right. It's top of it. So the surface in that corresponds to the surface of the soil column that you want to include in your SSI analysis. That consistency is what we have to maintain.
So what you have to do is you have to explain that there's really two PBSRS. There's one that's a grade elevation
and one on top of the soil column. Yes. So we'll go over the text of the SSR, and of course, as needed, we'll clarify that further. So that's mainly the main reason for all these assigned discrepancies. And so the NEI check for the partial column pairs is performed consistent with the use of partial pairs in SSI analysis, meaning that for the partial column outcrop pairs, we use partial column, 4 layers are removed. That's in a lower bound and upper bound profile.
So what is the development task for partial embedding?
For which building?
Partial
for the reactor building, I think it's between elevation 273.
We have a slide that shows all this.
120,
So it's 16, 17 feet for reactor building. Right. For control building is a little bit more, I think.
Yeah, it's half.
So the actual building is embedded in the rock, like 17 feet.
No. The soil part on the top is 17 feet.
Oh, I thought the partial embedding was you only consider the rock.
Right. So the rock embedment, I think, for reactor building goes from 273 all the way to 224. So So that's almost 50 feet of embedment.
It's quite a big,
These are the actual values, actually. So the reactor building is
Oh, shoot. Well, that was,
I will go back.
we'll show you.
The quirk here, or an extra complication, is the fact that when you do all the site response for the reactor building, you also take into account the control building profile, which is different from the reactor building profile. Is that explanation still valid when you consider that?
So what we did, this is in developing the FAIRs. We considered two soil columns. One was for reactor building control, RBSD. One was for control building. The RBSD profile includes all the boreholes, velocity measurement boreholes at the site. And we discussed this. That's the same profile that is used for GMRS, essentially. The control building has only the profile, the borehole, which is within its footprint. So we considered both of them. Then when we calculate GMRS and FAIRs for either of these buildings, we looked at the response coming from both soil columns. And we saw that at the bottom of reactor building, the response from the RBSB was actually controlling, except that something around 4 or 5% exceedance at high frequency that was coming from the CB profile. So we enveloped the two as a measure of conservativeness. At the CB control point, again, as a measure of conservativeness, we enveloped the two, but what happened was that the CB profile was already controlling the response by quite a large margin. So by enveloping the two, we were not adding too much undue conservatism to our design, but on the same breath, we could also say that we considered the site fully and we considered all the possibilities.
So for computing spectra,
That's what
you
we did.
envelop it too. But now when you're considering strain iterated profiles,
We go with the profile for
separate the
yeah,
two, so you don't mix them up.
exactly.
Okay.
And because that exceedance was, so for each one, its own corresponding profile was controlling, the strain compatible profiles are correct because we are not making up a much larger spectra that all of a sudden our strain compatible profiles are not. So,
they use all three profiles. For buildings, for foundation response sector, as I recall, they use three different versions.
for the three.
And basically, as far as I understood, they use the closest profile. If they have profiles just under the building, there is no need to further. Yes, but if it is somehow should be combined, they combine. That's my understanding.
So that's for spectra.
For spectra.
Now,
For the profiles, we go based on the profile for each field.
so you don't,
We don't mix.
still consistent because what you're saying is that any contribution from the others spectra
Is very.
Okay, all right.
I think we addressed the first 3 points here. We talked about surface, which means the surface of the profile that is being used in the SSI analysis. And for part D, which was asking whether or not to use in situ properties or the backfield properties, of course, consistent with our first calculation for the NEI check, we also use the in situ material. So that's, and we'll provide all of these in the next. The next question was, the question was stating that for FWSC, the concrete field below the base mat is represented as an integral part of the structural model used in the SSI analysis. And the question was asking, provide justification for defining control points at bottom of base mat and not bottom of the concrete field. If defined at the bottom of concrete field, the question stated, the combined structure is embedded and NEI check should be applicable through the fire water service company. The second part of the question was asking FWC has similar soil column compared to control building. In comparison with CD FIRS, explain why FWST FIRS has significantly lower amplitude and is shifted toward the lower frequency. In response, for the first part of the question, as we discussed before in question B, we say that the concrete field is considered a local site feature and it's explicitly included in the finite element model of the SSI analysis. But its inclusion in the SSI analysis does not make it part of the structure, as for the definition of the structure. In fact, the use of bottom of foundation as the control point is justified because, first of all, in both ISG 17 and NEI white paper, they define the FIRS at foundation elevation of the structure. They're very specific about that. It is also at that elevation consistent with the DCD definition, such that the comparison of the CSDRS that is calculated and that is used in DCD for FWST and the site-specific FIRS that we calculate for this building are meaningful. That comparison is applicable. The concrete fill material is not an integral part of the structure. It's considered as a very competent factory material, essentially. It has lower bound depth estimate and upper bound velocities, just same as soil, and those are 6,000, 7,000, 8,000 feet per second, and those are included. This concrete fill will be placed after removal of the saprolite and weathered rock in the footprint of the building. By weathered rock, we mean the zone 3 rock. And between the bottom of foundation and top of zone 3-4 rock. So the exact thickness of this concrete fill material will be determined as part of the construction. You see where you hit the zone 3-4 rock, and that concrete fill thickness will be non-uniform. On the other hand, bottom of foundation for FWST is at elevation 282 with the building. So again, consistent with the definitions in RSG 17, NEI white paper, and DCD, we are calculating the FIRS at the foundation elevation in the in situ material and at the pre-field.
So my comment on this is, I understand you had a almost identical situation in other cold calculations. They took essentially the approach that you're stating here, and they considered, or it was considered that the kind of building is part of the soil and not part of the structure. Then you have to consider the following. When you develop your FIRS, develop your site responsibility. Now you have a portion of material that's significantly different than the in-situ material. So it can't be shaped. You got to consider two-dimensional effects to capture significantly different properties of this material that is two-dimensional.
Absolutely. Absolutely. It is included explicitly in the SSI model in 3 dimensions.
Yes, but that would be represented in the FIRS.
But the FIRS is in the pre-field.
Not when you have this chunk of material now that's part of your soil.
And things
It
can
should be exactly the way you see it is, I mean, this is a very stiff material, right? So whatever high frequency input is coming in from the rock is going to go through that material, and it's going to reach your foundation elevation. And you're going to see that as high frequency content at first, and we don't see that in the airport.
So
That's the filter out. Yeah, the first is filtering it out.
let me try to respond to it a different way. If we were to calculate the FIRS at bottom of the field, let's say that for the sake of argument, bottom of the concrete field is a set elevation, right? Top of zone 3-4 rock. It's not in reality. There is going to be some variation within the footprint of the building. Let's say that we know what that elevation is. If I calculate the FIRS at that elevation and then do my analysis, I would still have to show that the motion that comes at the foundation elevation of the building to the structure satisfies my probabilistically calculated foundation. It's similar to the NEI check that you would have to do it at the surface, you would have to do it at the actual foundation. Not only that, if there is a difference in the frequency content of the motion on top of rock, versus the foundation elevation for the building. That difference in the frequency content is taken care of in the SSI model, in my lower bound estimate, upper bound properties. As I go from my first application in the SSI model down to the top of rock in the site, in the free field of the SSI model, and then that motion gets transmitted to the building. So there is not really a filtering that happens. That site response analysis happens in the SSI space as opposed to in the free field space. The real difference is that one is done probabilistically, one is done deterministically.
I think on this whole person okay. Nobody right now is doing true DNA. Everybody are using SAFE. Now, there are different ways of, I know it's not right, but it's a way that industry works and actually everybody works. What they do usually, one way, they take different profiles and they kind of envelope site amplification from one and another with certain ways. That's what I saw being done. But realistically, 2D analysis or 3D analysis instead of SAFE is only done in certain papers and actually has never been verified. Sample, no, I think that's a sample issue. That's an issue about 2D.
In the other
The
motion,
motion-
the other COLA,
Let me have
the same situation.
I think you're citing, I have to do something on the white paper, not in the right copy. Okay, I'll tell you what. Okay. You propagate, your motion propagates from the rock. You start with a rock motion, right? And this is off the profile. If you use the site response analysis, you don't have concrete field. Okay. So the rock motion, you're going to filter through the soil. Okay. All the high frequency amplification is going to go like that. Okay. But if knowing you have a chunk of concrete field, you have a thermal conflict in the wall. Now you put that between the space between the rock and the foundation. Okay. So the high frequency component is not going to be filtered out. They're actually going to be transferred. They'll be transferred directly to the foundation. Right? So, I mean, you can do either way. Okay, if you include the concrete field as a part of the free field, okay, you can carry that through the probabilistic analysis. So the higher frequency component will be enhanced. Okay. Or you can, the way you model it, as I said in the beginning, you model the whole thing as a part of the structure. So that's important. That's a definition, right? Once you define a structure, the foundation is identified, okay? The foundation is always at the bottom of the structure, okay? I mean, the ADI definition, I assume they're all based on site approach, okay? So the structure means the foundation is the bottom of the structure. Okay, if your concrete field is a part of the site structure now, then your foundation is the bottom of that structure. Okay. Now if you want to say, okay, I developed my definition of the foundation of my real structure, not a concrete field, right? My real structure. Then you need to develop a compatible motion at the foundation level, which is the bottom of the concrete field. Okay. So there is a process for doing that. Okay, you can do that. Okay, you can do that transfer. That's to that level. Okay, whatever fits in the field level, right? At the bottom of the concrete field. Okay. By doing that, you recover the high frequency amplification that being filtered valve in the process of development. Okay, so you want to recover that portion, and then you apply that motion, that will be your control motion for the SSI, and that will be consistent with SSI methodology. Okay, otherwise they're inconsistent. Okay, you basically, I mean, the reason we would like people to develop motion at foundation level is because of this deconvolution issue, right? You know, if you have motion, specified at the elevation that is higher, that is above the foundation level, what's going to happen is in the process of the SSI, when you calculate the foundation level motion, there's going to be de-amplification at the column surface, right? And that de-amplification, you know, depends on the path between your control point and foundation level, may become unrealistic and not physically, realized, right? So it's no longer, you know, in the physics point of view, it's no longer be realistic. Okay, and that's the reason we don't want people to do the deconvolution. It doesn't matter whether explicitly or implicitly.
Right. I do understand your concern. I agree with that is concern. What we can do is we can show, you know, by doing the analysis, calculating the motion on the bottom of the field probabilistically, and compare it to the motion coming from SSI model at the bottom of the field. And then if we can show that that motion from the SSI model exceeds the motion, probabilistic motion at the bottom of the field, that should answer this concern.
I think it's a complicated because if you're going to do it probabilistic analysis, how are you going to account for the two uses?
No, what you just asked us to do was to calculate the foundation, the fares, at the bottom of the field, right?
In order to transfer first up and down, you use the total column.
So in the sort column analysis,
You have
No. The stick material is considered part of structure. Okay? That's part of
what we
structure.
would do.
No. That's exactly how they model. Okay? So right now the issue is where you put the motion, how you put the motion. That motion is still free field issue. It's not a advertising issue. Okay. You can transfer that first from where you calculate at a structural foundation level. Okay? To the bottom of the concrete field. Okay. If you do that,
compare that motion with what is calculated in the deterministic SSI analysis on bottom of the field. So that's what is used in the SSI analysis. Why not?
Because your SSI analysis should use that as an input. Okay, if your SSI analysis use the first based on your calculated current foundation level, the SSI analysis won't. The SSI analysis is not going to be right because that SSI analysis implicitly includes the deconvolution process. So basically deconvolve to the foundation.
The reason you are calling it wrong is that the high frequency portion of the motion will not be represented. Right? That's your concern. That's your concern. So if we can show that high frequency portion is there, or change our pairs such that high frequency motion be there, then that concern goes away.
If you do your first at the bottom of the concrete, like standard technical UAV do, and then you apply that and show that that's conservative somehow, whatever you're doing currently, that should be okay.
So basically what you suggest is developing you first at the concrete bottom, running the analysis, and see how the result will be.
How the results change, okay? I mean, you just apply your standard method first. Get to that.
Right, but can we do this in the site response part of it? Meaning without the
Site response.
We don't have to do this.
Other places, you develop at the bottom of that concrete, develop the first at the top, at the bottom of, Top of rock, right? Or
top of rock.
Top of rock.
Of course, the complication there is that top of rock is varies, right? So we would have to make best estimate depth assumptions.
Another issue we will have, I mean, this is from the regulatory point of view, the DCD requires, and then when we refer to ISG 17 NEI, requires us to compare the first at the same elevation that CSDRS was calculated.
I know you didn't consider the first, right? You compare the first. You compare the first, but now you have experiences, okay? If your first does not have experience, you have no problem, right? And you don't need to go further, right? Now, because you compare the first, you have experiences, now you have to get into a structural response. That's why you involve SSI, right? So to do the SSI right, you have to make sure you're controlling.
So you realize if we calculate first on top of zone 3-4, it's going to be much lower than what we have.
No, but the elevation is low.
The elevation is so we can't do a one-to-one comparison anymore.
Right, because, I mean, the CSDRS, for example, in the DCD for fire water service complex was multiplied by factor to show that there is some amplification due to the fact that it's higher.
Well, that comparison with the DRS is out the window now because already shown that it's repeated, right? How do you, all you have to do is have to be done right.
But you're asking me to calculate another first for this.
And then putting it in the structure and seeing what the structural response is.
But we still need the first, right? For the
It's a control motion consistent with the first. The same definition as like we use for the first. The first is actually what is the motion calculated at the foundation level at outcrop, but consistent with GMRS.
But, you know, still, I mean, there is a confusion coming from my point of view, from ISG 17. Because ISG 17 defines, allows to basically calculate foundation input response factor in two ways. And they choose to do one way, which was pushed long time ago by Bachand. That's the way they do it. In some other places, applicants are doing this in a way you are basically no effect of upper part, just input below concrete foundation. It's much more easy, no more that.
Two different things, two different issues, okay? You need to calculate, you want to follow ASCII sum. The first step is calculate the first at the foundation level, not at the bottom of the complicated, at foundation level, right? And you compare that to, you know, you compare it. But if your first is that low, then you don't go further, right? You're done, right? But if you have experiences, then you go to the next step, which is the SSI. The full SSI nothing to do with, you know, with this part. You have to make sure the neutral motion is correctly applied on the bottom.
Okay,
May I paraphrase what I think I heard you say, was that to calculate first, the way we have it, so the first that we already calculate in section 2.5.
Right, and you already experienced, right?
And that's the first that you would include. Right. But then you would want us to calculate a different spectra, now SSI input response spectra, at a different elevation than first, and then use that in the analysis.
The first transfer to that level.
But it's not really transferred because it's not done in 3 profiles. It has to be calculated similar to first probabilistic,
We would
right?
consider that as consistent, right? You know, the way we transfer first is the GMR to transfer to the foundation, right? But actually, there are no correspondence of the determinant. So in the probabilistic way, they correspond, right? They're both at the 60 profiles and started with the same UHS, right? And then you go through probabilistic process and then you just calculate different levels, okay? But you cannot go from one motion to the other motion, so they don't have direct the term earthquake one-to-one correspondence. They are probable earthquakes for a